November 14th, 1942, 11:17 p.m. The darkness over Iron Bottom Sound near Guadalcanal was absolute. No moon penetrated the thick tropical clouds. Aboard the battleship USS Washington, Rear Admiral Willis Augustus Lee stared at something that would have been impossible to imagine just 5 years earlier. On the glowing radar screen before him, ghostly electronic echoes revealed Japanese warships 18,000 yards away, completely invisible to the naked eye in the pitch-black night. Admiral Lee was a unique commander for his time, a former Olympic gold medalist in shooting. He possessed an unusual fascination with technology that many of his contemporaries dismissed as theoretical nonsense. But Lee understood something profound. The electromagnetic radiation bouncing off those Japanese ships and returning to his antennas represented more than detection. It represented the future of naval warfare. At 11:17, Lee gave a simple command: open fire. The 16-inch guns of Washington thundered, hurling 2,700-pound armor-piercing shells into the darkness toward targets no human eye could see. The Japanese had no idea they were under attack until the first salvo landed near the light cruiser Sendai. For the first time in naval history, a battleship was engaging an enemy fleet using only electronic eyes, firing at ships beyond visual range in complete darkness. This moment marked a revolution as profound as the introduction of the cannon to naval warfare. For thousands of years, naval combat had been limited by human eyesight. You could only fight what you could see. But on that November night in 1942, American technology shattered that ancient limitation. The marriage of radar and mechanical computing had created something unprecedented: the ability to find, track, and destroy enemy warships that existed only as electronic phantoms on a cathode ray tube. The path to this revolution had begun decades earlier, not in response to war but from a humiliating realization. During the Battle of Jutland in 1916, the British Royal Navy, considered the finest fleet in the world, discovered that despite possessing superior ships and gunnery training, only 3% of their shells actually hit German vessels. 3 shells out of every 100. The problem was not courage or training, it was mathematics. Naval gunnery represented one of the most complex ballistic calculations ever attempted. Both the firing ship and the target were moving independently, often at different speeds and on different courses. The projectile itself required 20 to 40 seconds of flight time to reach a target at maximum range. During that time, the target could move more than 1,000 yards. The Earth's rotation introduced Coriolis effect, causing shells to drift. Wind deflected the projectile. The ship firing the gun rolled and pitched on ocean waves. Temperature affected powder charge performance. Barrel wear changed muzzle velocity. Even the density of seawater at different locations affected splash, patterns used for ranging. Solving this equation required predicting where a moving target would be 30 seconds in the future, while accounting for dozens of variables, all while your own ship pitched and rolled beneath your feet. Human gunners working with simple rangefinders and manual calculations simply couldn't process this information fast enough. By the time they calculated a solution, the tactical situation had changed. The US Navy's answer to this problem came from an unlikely source: Hannibal Choate Ford, a Georgian-born mechanical genius who had shown talent with clocks and watches as a young boy. Ford founded the Ford Instrument Company in 1915, not to build automobiles, but to construct mechanical analog computers. These were not electronic devices. They were intricate assemblies of gears, cams, shafts, and differentials that could perform complex mathematical calculations through purely mechanical means. Ford's first major naval contract came in 1916 when the Navy commissioned development of the Mark I Rangekeeper. The name itself was telling. This device didn't just calculate range to a target, it kept continuous track of that range as it changed second by second. The concept was revolutionary. Instead of taking a single measurement and calculating where to aim, the Rangekeeper created a dynamic simulation of the tactical situation that updated continuously. The heart of Ford's invention was a mechanical marvel called a ball and disc integrator. Picture a flat disc about 6 inches in diameter, spinning at constant speed like a record player. Pressed against this disc was a smaller ball, about 1 inch in diameter. A mechanical carriage could move this ball from the center of the spinning disc to its edge. When the ball sat at the disc's center, it didn't rotate because there was no tangential motion. but as the carriage moved the ball toward the disc's edge, the ball began to rotate. The farther from center, the faster it spun. This simple mechanism performed mathematical integration. The spinning disc represented time passing at a constant rate. The position of the ball represented a rate of change like target speed. The rotation of the ball produced the integral of that rate, giving you the change in position over time. Multiple integrators could be connected through gear trains to solve complex differential equations entirely through mechanical motion. The Mark I rangekeeper installed on USS Texas in 1916 was primitive by later standards. It weighed about 2,500 pounds and required multiple operators to input data manually. But it could do something humans couldn't. It could continuously solve the equations of motion for both your own ship and the enemy, predicting future positions and automatically updating gun aiming solutions. When you locked onto a target, the rangekeeper didn't just tell you where to aim now, it told you where to aim to hit where the target would be when your shells arrived. But early rangekeepers had a critical limitation. They calculated gun angles automatically, but humans still had to manually turn the guns to match those angles. Sailors called this pointer following. An operator watched a needle on a dial showing the correct angle. He then turned a handwheel to rotate the gun until a second needle lined up with the first. This system worked, but it was slow and introduced errors. During extended battles, exhausted crews made mistakes. Targets could change course between the time the rangekeeper calculated a solution and the time the gun actually reached the correct angle. The breakthrough came in the 1930s with the development of servo mechanisms. Electric motors connected directly to the gun mounts could automatically slew the massive weapons to the angles calculated by the rangekeeper. The Navy called these power drives. Once you locked onto a target, the system created a closed loop. The rangekeeper calculated the correct angles. The servo mechanisms moved the guns. Sensors on the gun mounts fed the actual position back to the rangekeeper. If the gun wasn't quite at the correct angle, the error signal caused the motor to correct. The guns became enslaved to the computer's commands. By the late 1930s, the US Navy had developed the Mark 8 rangekeeper, a masterpiece of mechanical engineering. Weighing over 3,000 pounds, it contained approximately 20 servo mechanisms, hundreds of gears, dozens of differentials, and numerous ball and disc integrators all working in perfect synchronization. One operator could input target course and speed. The computer automatically calculated range rate, bearing rate, and the deflection angles needed to hit a moving target. It accounted for your own ship's motion, using inputs from gyroscopic sensors that maintained a true vertical reference, even as the ship rolled and pitched. The Mark 8 could track a target even if it temporarily disappeared from view. Because it maintained a dynamic simulation of the target's motion, losing visual contact for a few seconds didn't matter. The computer continued predicting where the target should be. When the target reappeared, you could quickly verify the solution was still valid. But mechanical computing alone couldn't break the fundamental limitation of visual range. Even the best optical rangefinders, with baselines stretching 40 feet or more, could only measure distances out to about 25,000 yards in good visibility. At night, in fog or in smoke from battle damage, effective range collapsed to a few thousand yards. Ships could carry the most sophisticated fire control computers ever built, but they were useless if you couldn't see the target. Radar changed everything. The development of microwave radar in the early 1940s, particularly the Mark III and later Mark 8 fire control radars, gave ships electronic eyes that could pierce darkness, fog, and smoke. But radar did more than just detect ships. It could measure their range with precision impossible for optical systems. The Mark 8 radar operated at wavelengths around 3 centimeters, producing a narrow beam that could be precisely directed. When this beam struck a ship, some energy reflected back. By measuring the time delay between transmission and reception, the radar calculated range with accuracy measured in yards from over 40,000 yards away. More sophisticated signal processing could determine not just where a target was, but how fast it was moving and in what direction, by analysing how the return signal changed over multiple sweeps. The critical innovation came from integrating radar and mechanical computing. The Mark 8 fire control system connected radar range and bearing data directly into the Mark 8 rangekeeper. The computer received continuous updates on target position without human intervention. An operator no longer needed to manually crank in range estimates. The radar did it automatically, feeding precise measurements to the computer 30 times per second. This integration created what modern engineers would call a feedback control system. The radar detected the target and measured its position. The rangekeeper calculated where the guns should point. Servo mechanisms moved the guns to that position. The guns fired. The radar tracked the shell splashes and measured how far off they were from the target. This error information fed back into the rangekeeper, which automatically corrected its solution. This cycle repeated continuously, with each salvo becoming more accurate as the computer refined its understanding of the ballistics. The Mark 8 system could establish what fire control officers called a hard lock on a target. The narrow radar beam, combined with sophisticated filtering in the rangekeeper, allowed the system to track a single ship even when multiple vessels were in proximity. Shell splashes, which created radar returns that could confuse earlier systems, were automatically filtered out because their signatures were different from solid metal ships. For the first time, a battleship could engage targets in complete darkness at ranges exceeding 20,000 yards with accuracy comparable to daylight operations. This was beyond horizon combat. At 20,000 yards, about 11 nautical miles, the curvature of the Earth meant that a target ship sitting low in the water was physically invisible to observers on another ship's deck. The target existed only as electronic echoes. The USS Washington's engagement on November 14, 1942, demonstrated this capability in combat. After Admiral Lee's initial salvos at the Sendai Group, his radar operators acquired a larger target. The returns indicated a capital ship, range 18,400 yards and closing. The Mark 8 radar was locked on. The rangekeeper began calculating a fire control solution. At 2358 hours, Washington's plotting officers identified the target as the battleship Kirishima. The Japanese ship was illuminating USS South Dakota with searchlights, completely unaware that Washington had acquired a radar lock on her from nearly 10 miles away in total darkness. South Dakota had suffered electrical failures that knocked out her radar, leaving her blind and silhouetted by Japanese searchlights. But Washington's electronic eyes never blinked. At 2400 hours, at a range of 8,400 yards, Washington opened fire. Her first salvo straddled Kirishima, shells landing both short and over. The rangekeeper automatically adjusted for this error. The second salvo, fired just 45 seconds later, scored direct hits on Kirishima's superstructure, obliterating her bridge and killing everyone in it. The third salvo was devastating. 5 16-inch armor-piercing shells struck the Japanese battleship amidships. One penetrated below the waterline. Flooding began immediately. Washington fired 9 salvos in 3 minutes, 75 rounds of 16-inch ammunition. Kirishima never got a single shot off at Washington. She couldn't. Her fire control systems required visual target acquisition, and she couldn't see Washington in the darkness. By the time Japanese searchlights found the American battleship, Kirishima was already doomed, listing heavily and on fire. The engagement lasted less than 7 minutes from first radar contact to ceasefire. In that time, American fire control technology had achieved what Jutland had demonstrated was nearly impossible: a hit rate exceeding 15% against a maneuvering target at night. More significantly, Washington had fought a battle where she could see her enemy electronically, while remaining invisible to visual detection. One-sided battles like this changed naval warfare forever. The Japanese Navy never developed comparable technology. Their fire control systems relied on optical rangefinders and manual calculation. Japanese commanders had drilled their crews in night fighting extensively, using visual recognition and training to achieve what they couldn't accomplish with technology. But human eyes, no matter how well trained, couldn't penetrate complete darkness at ranges exceeding 10,000 yards. Japanese ships were technologically blind in the very conditions where American vessels saw with perfect clarity. The true culmination of American fire control technology came almost 2 years later, at the Battle of Surigao Strait on October 25, 1944. This engagement would prove to be the last time in history that battleships fought battleships with their main guns. It was also the most one-sided gunnery engagement in naval history, a demonstration of how completely American fire control technology had outpaced anything else afloat. Vice Admiral Shoji Nishimura's Southern Force approached Surigao Strait with 2 battleships, the Fuso and Yamashiro, 1 heavy cruiser Mogami, and 4 destroyers. Their mission was to break through into Leyte Gulf and attack American amphibious forces supporting the Philippines invasion. Waiting for them in the narrow strait was Rear Admiral Jesse Oldendorf's fire support group, 6 American battleships, 8 cruisers, and 28 destroyers. 5 of Oldendorf's 6 battleships had been at Pearl Harbor on December 7, 1941. Some had been sunk in the shallow harbor and raised from the mud. West Virginia, California, and Tennessee had undergone complete reconstruction. Their old cage masts and outdated fire control systems had been ripped out and replaced with the most advanced technology the United States could produce. Each received the Mark 8 fire control radar and Mark 8 rangekeeper computer system. This was revenge in the most literal sense. Ships that had been destroyed by Japanese surprise attack, rebuilt with technology that made surprise impossible. Oldendorf deployed his forces brilliantly. He positioned his battleships in a line running east to west across the northern exit from Surigao Strait. This was the naval tactician's dream. Crossing the T-enemy ships advancing northward through the strait could only bring their forward turrets to bear, while American ships running perpendicular could fire full broadsides. But Oldendorf's advantage went far beyond formation. His ships could see electronically while the Japanese were blind. As Nishimura's force ran the gauntlet of American destroyers and PT boats, torpedoes found Fuso, breaking her in half. But Yamashiro continued onward with Mogami and a single destroyer. The Japanese admiral pressed his attack, expecting to engage at close range where Japanese training in night fighting would give them an advantage. He had no idea he was steaming into a death trap. At 3:02 hours, Tennessee's search radar picked up Japanese ships at 44,000 yards. This was 22 nautical miles, well beyond visual range even in daylight. The target was invisible. It existed only as electronic returns on a cathode ray tube. 14 minutes later, at 03:16, West Virginia's radar acquired the target at 42,000 yards. The plotting room crews went to work. The Mark 8 rangekeeper computers began calculating firing solutions. The ranges involved were staggering. At 42,000 yards, about 24 statute miles, the shell would be in flight for over 40 seconds. During that time, both ships would move. The projectile would rise to an apex exceeding 50,000 feet altitude before plunging down at terminal velocity. Wind at multiple altitudes would affect trajectory. The Coriolis effect became significant at these ranges. The fire control computer had to account for all of this, predicting where both the target and the shells would meet in space and time nearly a minute in the future. At 0351, Oldendorf gave the order to commence firing. West Virginia opened fire first at 0352, at a range of approximately 22,800 yards. Her first salvo of 4 16-inch shells arced into the darkness toward a target no one aboard the battleship had seen with human eyes. The radar tracked the shells in flight, then tracked the splashes. The returns showed the salvo had straddled the target. The rangekeeper automatically corrected. The second salvo, fired 40 seconds later, scored hits. Tennessee and California joined the bombardment at 0355. 3 American battleships, their fire controlled entirely by radar and mechanical computers, were systematically destroying a Japanese battleship that couldn't even see them. Yamashiro's optical rangefinders were useless in the darkness. Her fire control team had no idea where the American ships were. They fired back blindly in the general direction of muzzle flashes, but their shells fell nowhere near the American line. The engagement was surreally one-sided. Yamashiro was being torn apart by shells arriving from invisible sources. Radar-directed American fire was achieving hit rates between 15 and 20%, extraordinary accuracy considering the darkness, range, and maneuvering target. The Japanese ship was burning, flooding, and losing steering control within minutes of the first American salvos. By 0359, Maryland, equipped with the older Mark III radar, had also acquired a target and opened fire. The battleships were now firing synchronized salvos, with shells from multiple ships converging on Yamashiro simultaneously. The Japanese battleship was experiencing what no warship in history had endured before: precision bombardment from beyond visual range in complete darkness by an enemy she couldn't locate, couldn't range, and couldn't fight back against. West Virginia alone fired 93 rounds of 16-inch ammunition during the engagement, more than any other battleship present. Her Mark 8 fire control system had maintained a solid radar lock on Yamashiro throughout the battle, even as cruiser gunfire created shell splashes all around the target. The sophisticated signal processing in the Mark 8 radar could distinguish the solid return of a steel ship from the transient splashes of near misses. At 04:05, Yamashiro took a final torpedo hit from the destroyer Benyon. She was already doomed from the gunfire. At 04:19, the Japanese battleship suddenly capsized and sank, taking Vice Admiral Nishimura and most of her crew down with her. From first radar contact at 0302 to Yamashiro's sinking at 0419, just 77 minutes had elapsed. In that time, American fire control technology had achieved what military theorists had long dreamed of but considered impossible: decisive engagement at ranges where the enemy was physically unable to fight back. The Battle of Surigao Strait lasted only about 15 minutes of actual gunnery action. The 6 American battleships fired approximately 285 shells of 14-inch and 16-inch caliber. Hit rates exceeded 10%, extraordinary for night action at moving targets. The 8 American cruisers fired over 2,000 shells of 6-inch and 8-inch caliber. The Japanese force was annihilated. 2 battleships sunk, 1 cruiser crippled and later sunk, 3 destroyers destroyed. Not a single American ship was hit by Japanese gunfire. The disparity wasn't about courage or seamanship. Japanese sailors were brave and their ships were well designed. The difference was technology. American warships fought with electronic eyes that could see through darkness and fire control computers that could predict the future. Japanese warships fought with human eyes and manual calculation, exactly as navies had for centuries. It was like bringing swords to a gunfight. The psychological impact on Japanese survivors was profound. Sailors rescued from Yamashiro reported that the experience was terrifying. Shells arrived from nowhere, impacting all around their ship. They couldn't see muzzle flashes. They couldn't determine range or bearing to the enemy. They were being systematically destroyed by invisible attackers. Some survivors initially believed they had been struck by submarine torpedoes or aircraft, unable to comprehend that they were being bombarded by surface ships firing from beyond the horizon. After Surigao Strait, Japanese naval strategy began emphasizing suicide attacks. Part of this was desperation as their situation became hopeless, but part was a rational assessment that conventional naval gunnery engagement against the American fleet was suicide. American fire control technology had achieved such dominance that any surface action would be one-sided slaughter. The kamikaze represented a weapon that didn't require sophisticated fire control. A pilot could see an aircraft carrier with his own eyes and aim his plane at it manually. Human courage could potentially overcome technological inferiority. The development and deployment of American fire control technology represented one of the most successful military research and development programs in history. From the initial Mark bomber rangekeeper in 1916 to the Mark 8 system in 1943, the evolution took less than 30 years. During that time, the United States transformed naval gunnery from an art practiced by experienced gunners into an automated science performed by mechanical computers. The numbers involved in producing these systems were staggering. Ford Instrument Company, working with contractors including IBM, Sperry and others, produced over 1,200 Mark I and Mark IA fire control computers during World War II. These were installed on virtually every destroyer, cruiser and battleship in the US Navy. Each computer was a precision instrument containing thousands of parts machined to tolerances of thousandths of an inch. Building one required approximately 3,000 man-hours of skilled labor. The Mark 8 rangekeeper computers for battleship main battery control were even more complex. Each unit required over 5,000 hours to construct and cost approximately $1.2 million in 1943 dollars, equivalent to over $20 million today. But the investment paid for itself in combat effectiveness. A single battleship equipped with Mark 8 fire control could engage and defeat multiple opponents lacking equivalent systems. The success of mechanical fire control computers influenced post-war development of electronic digital computers. Engineers, who had worked on rangekeepers, went on to design early electronic computers in the late 1940s and 1950s. They brought with them concepts like feedback control, automatic error correction, and real-time data processing. The fire control problem, requiring continuous solution of differential equations with multiple variables, helped drive the development of computational techniques that would become foundational to modern computing. The Rangekeeper systems remained in US Navy service far longer than anyone expected. The Mark I computer, first deployed in 1916, saw action in World War II and remained operational on some ships until the early 1960s. The Mark IA, developed during World War II, stayed in service through the Korean War and Vietnam War, only being retired when the last gun-armed cruisers were decommissioned in the 1970s. These mechanical computers, built with 1940s technology, continued solving gunnery problems effectively for 3 decades after electronic computers became available, testament to the sophistication of their design. Several preserved battleships serving as museums today, including USS Alabama, USS Massachusetts, and USS North Carolina, retain their original Mark IA fire control computers in place. Visitors can see these mechanical marvels, though few realize they're looking at some of the most sophisticated analog computers ever built. The intricate assemblies of gears and cams sit silent now, but in their time, they gave American warships the ability to reach beyond the horizon and strike with precision that seemed almost magical. The legacy of naval fire control computers extends beyond military applications. The techniques developed for automatically tracking targets and predicting their future positions found civilian use in air traffic control, missile defense, and eventually in autonomous vehicle navigation. The concept of sensor fusion, combining data from multiple sources to create a unified picture of reality, first implemented in integrating radar with mechanical computers, now underlies everything from smartphone cameras to self-driving cars. But at their core, fire control computers represented something profound about how technology changes warfare. For thousands of years, combat at sea was limited by human sensory capability. You could only fight what you could see, and you could only aim where you could observe. The introduction of radar and automatic computing shattered these limitations. Ships could fight in complete darkness. They could engage targets dozens of miles away. They could predict the future with mathematical precision. The Japanese Navy at Surigao Strait wasn't defeated by more ships or bigger guns. American battleships were actually older, and in some cases less heavily armed than their Japanese opponents. They were defeated by mathematics, by mechanical computers that could solve differential equations faster than human calculators, by radar that could see through darkness, by servo mechanisms that could aim guns with mechanical precision. The battle demonstrated that in modern warfare, technological superiority could overcome every other factor. When USS West Virginia led the American battle line at Surigao Strait, she was in a sense completing a journey. 3 years earlier, she'd been on the bottom of Pearl Harbor, torn apart by Japanese torpedoes, her crew dead or scattered. American salvage teams raised her, cut away her damaged sections, and rebuilt her from the waterline up. They installed the most advanced fire control system in the world, technology that Japanese engineers hadn't even conceived of. On October 25th, 1944, this resurrected ship, guided by mechanical computers and radar, systematically destroyed a Japanese battleship from beyond visual range in total darkness. The symbolic weight of that reversal was not lost on the American sailors who had survived Pearl Harbor. The fire control officer aboard West Virginia that night later wrote that watching the radar track shells in flight and then watching them hit a target he couldn't see felt like science fiction. The idea that machines could see and think faster than humans, that electronics and mechanics could perform tasks impossible for any human, was still novel in 1944. We take it for granted now. Every smartphone contains computing power that dwarfs what the entire Mark 8 system could achieve. But in that moment, in the darkness of Surigao Strait, it was revolutionary. After the battle, Admiral Oldendorf reported to his superiors that American fire control systems had performed flawlessly, enabling his ships to engage and destroy enemy battleships at ranges and under conditions previously impossible. He specifically credited radar-directed fire with achieving the decisive results. Japanese survivors interrogated after the war confirmed they had been unable to locate American ships during the engagement, and that incoming fire seemed to arrive from impossible ranges. The Japanese Navy did possess some radar systems by 1944, but they were primitive compared to American equipment. Japanese radar could detect ships at reasonable ranges, but it couldn't provide the precision range and bearing data needed for fire control. Japanese fire control computers were also less sophisticated, requiring more manual input and providing less accurate predictions. Most critically, Japanese systems weren't integrated. Radar, optics, and computing remained separate systems requiring human operators to manually transfer data between them. American systems were fully integrated. Radar data flowed directly into the rangekeeper. The computer controlled the gun's servo mechanisms. The entire system functioned as a unified whole with minimal human intervention required once the operator designated a target. This integration made American systems faster and more accurate, but more importantly, it made them work in conditions where Japanese systems failed completely. You couldn't manually transfer data from optical rangefinders if you couldn't see the target at all. The development of these systems reflected broader American advantages in industrial capacity and scientific research. Building a rangekeeper required precision machining capabilities that few nations possessed. The gears had to be cut to extraordinary tolerances. The ball and disc integrators required perfectly smooth surfaces. The servo mechanisms needed reliable electric motors and precise sensors. This required an industrial base capable of producing complex mechanical and electrical components in quantity while maintaining quality. The United States had that industrial capacity. American factories produced fire control computers by the hundreds, while simultaneously building ships, aircraft, tanks, and millions of shells for those computers to direct. The same precision machining capability that produced rangekeepers also produced the superchargers for B-29 bomber engines and the gun sights for P-51 fighters. American engineering education had produced thousands of mechanical and electrical engineers who could design and maintain these systems. The institutional knowledge to build and operate complex electromechanical systems was deeply embedded in American industry. Japan lacked this industrial depth. They could build sophisticated machines, but not in the quantities required. They had skilled engineers, but not enough of them. Training someone to maintain a rangekeeper required months of technical education. The US Navy ran schools specifically for fire control technicians, graduating hundreds of newly trained specialists every month. Japan couldn't match this investment in training and infrastructure. The result was that by 1944, American warships possessed capabilities that Japanese ships simply couldn't counter. The technology gap had become so wide that conventional naval engagement was essentially impossible for Japanese forces. They couldn't fight effectively at night. They couldn't engage at long range. They couldn't achieve hit rates sufficient to overcome American numerical advantages. The naval war in the Pacific became a series of one-sided engagements where Japanese courage and seamanship couldn't overcome technological inferiority. The ultimate irony was that Japan had started the Pacific War with one of the most technologically advanced navies in the world. Their torpedoes were superior to American weapons, their night-fighting doctrine was more developed, their optical rangefinders were excellent. But they had focused on perfecting existing capabilities, while the United States invested in fundamentally new technologies. When radar and automated fire control matured, Japanese advantages in traditional areas became irrelevant. This pattern has repeated throughout military history. Technological revolutions don't just improve existing capabilities, they make old advantages obsolete. The machine gun made cavalry charges suicidal. The aircraft carrier made battleship main guns secondary weapons, and radar-directed fire control made traditional naval gunnery skills nearly irrelevant. You could have the best-trained optical rangefinder operators in the world, but they couldn't compete with electronic systems that saw through darkness. For the sailors aboard American warships, the experience of using these systems was often surreal. Fire control technicians worked in plotting rooms deep inside the ship, staring at radar screens and adjusting computer inputs. They never saw the targets they were destroying. Gunners in the turrets loaded and fired shells at the computer's command, aiming at coordinates fed to them electrically, engaging enemies they couldn't see. The whole process felt removed from traditional concepts of naval combat. Some older officers initially distrusted the systems. They had trained for decades in visual gunnery, learning to estimate range by eye and judge target motion by observation. The idea of delegating these critical decisions to machines felt wrong to them. But the combat results were undeniable. Ships using radar-directed fire achieved hit rates 2 to 3 times higher than those relying on optical systems. In night engagements, there was no comparison. Optical systems failed completely, while radar systems worked perfectly. By war's end, every American naval officer accepted that fire control automation was the future. The question wasn't whether to use it, but how to make it even better. Post-war development focused on electronic computing to replace mechanical systems, more sophisticated radar to track multiple targets simultaneously, and eventually guided missiles that didn't require the ship to be aimed at all. But the fundamental breakthrough had been achieved in the mechanical systems of World War II. The concept of using sensors to detect targets beyond human perception, using computers to predict future positions, and using servo mechanisms to aim weapons automatically. This paradigm, first successfully implemented in the Mark 8 fire control system, underlies virtually all modern weapon systems. Modern aircraft, tanks, and ships all use variations on this approach. The specifics have changed. Electronics replaced mechanics, digital replaced analog, but the core concept remains the same. Standing on the deck of USS Washington on November 15, 1942, watching searchlights play across the burning Hiroshima, Admiral Lee understood he had witnessed something historic. For the first time, a battleship had fought and won an engagement where the enemy was never visible to human eyes. The engagement had been controlled entirely by machines. Radar had found the target. Computers had calculated the solution. Servo mechanisms had aimed the guns. Human operators had supervised the process, but the machines had done the work. This was the future of warfare. Not just naval warfare, but all warfare. The side with better sensors, better computers, and better integration would possess advantages that courage and training couldn't overcome. Technology had always influenced combat, but now it was beginning to dominate it. The sailors who had operated these systems during World War II often reflected later on how strange it felt. They had fought battles against enemies they never saw. They had destroyed ships that existed only as electronic blips. They had killed men who were invisible to them. This psychological distance would become characteristic of modern warfare. Today, drone operators sit in air-conditioned rooms thousands of miles from their targets. Soldiers view battlefields through thermal imagers and night vision systems. Ships engage enemies at ranges where visual identification is impossible. All of this traces back to those first radar-directed engagements in 1942 and 1944. The men who built these systems, engineers at Ford Instrument Company, Sperry, IBM, and other contractors, were not famous. Their names don't appear in most histories of World War II. But their work changed naval warfare more fundamentally than any tactical innovation or strategic decision. They took abstract mathematics, complicated physics, and precise mechanical engineering and turned them into weapons that could strike beyond the horizon. Today, naval combat has evolved far beyond what Admiral Lee witnessed. Modern ships use phased array radars that can track hundreds of targets simultaneously. Digital computers process information millions of times faster than mechanical rangekeepers. Guided missiles engage targets hundreds of miles away. But the principle remains the same. Electronic sensors detect what human eyes cannot. Computers predict what human minds cannot calculate. Automated systems engage at ranges where human skill becomes irrelevant. The fire control systems of World War II represented humanity's first successful attempt to create weapons that operated beyond human sensory limitations. They were the first true cyborg weapons. Human and machine intelligence merged into unified systems capable of achieving what neither could accomplish alone. A human operator designated the target and made the decision to fire. But machines found the target, tracked it, predicted its future position, calculated the ballistic solution, aimed the guns, and in some cases even decided when to fire based on optimal conditions. This partnership between human decision-making and machine precision proved devastatingly effective. At Guadalcanal and Surigao Strait, American fire control systems achieved decisive victories that changed the course of the Pacific War. Japanese forces could no longer contest American naval superiority in traditional gunnery engagements. The technology gap had become too wide. Every subsequent Japanese naval strategy had to account for this fundamental disadvantage. The development of these systems also represented one of the greatest achievements in mechanical engineering. The Mark 8 rangekeeper, built entirely with gears, cams, and mechanical linkages, could solve differential equations in real time while accounting for dozens of variables. It did this with perfect consistency, never making arithmetic errors, never getting tired, never losing concentration. Modern engineers examining preserved examples are still impressed by the sophistication of their design. In the history of warfare, certain technologies fundamentally change how battles are fought. The stirrup gave cavalry decisive advantage. Gunpowder made castles obsolete. The machine gun transformed infantry tactics. The aircraft carrier made distance irrelevant. Radar-directed fire control systems ended the age of visual naval combat. After Surigao Strait, it was no longer possible to fight a major naval gunnery engagement without possessing comparable technology. The era when human eyes and manual calculation could guide naval weapons had ended. The technical achievement represented by these systems becomes even more impressive when you consider the constraints under which they operated. Naval fire control computers had to function in some of the most hostile environments imaginable. They operated on ships that rolled and pitched continuously. They endured the violent shock of main battery guns firing just feet away, with each salvo generating forces measured in dozens of Gs. They had to maintain precision while exposed to salt spray, humidity, and temperature extremes ranging from Arctic cold to tropical heat. The mechanical design incorporated sophisticated shock mounting to isolate sensitive components from gun blast and wave impact. The entire rangekeeper assembly sat on a system of springs and dampers that absorbed shock while maintaining alignment. Critical components were hermetically sealed to prevent moisture intrusion. Bearings were preloaded to eliminate play that could introduce errors. Every gear was cut with precision that rivaled watchmaking. The tolerance for error was measured in thousandths of an inch, yet these machines worked reliably in combat conditions for hours or even days at a time. Maintenance requirements were substantial. Each rangekeeper required a dedicated team of fire control technicians who performed daily inspections, lubrication, and alignment checks. Before action, technicians would run diagnostic routines, manually rotating input shafts while verifying that outputs matched expected values. They checked synchronization between multiple gun mounts, verified that servo mechanisms responded correctly to commands, and confirmed that radar data was feeding properly into the computer. This level of technical maintenance was unprecedented in naval operations. The US Navy's investment in training fire control technicians paid enormous dividends. By 1944, the fleet had thousands of sailors who understood not just how to operate the systems, but how they worked at a fundamental level. These technicians could diagnose failures, perform field repairs, and even modify systems to address specific tactical needs. This expertise represented a strategic advantage as significant as the technology itself. You could give someone sophisticated equipment, but without trained personnel who understood it deeply, that equipment became useless. Japanese intelligence was aware of American fire control capabilities by late 1943. Captured documents and prisoner interrogations provided detailed information about radar and computing systems, but knowing about technology and possessing the industrial capacity to replicate it were entirely different matters. Japan lacked the precision, machining infrastructure, the trained workforce, and increasingly as the war progressed, the raw materials to build comparable systems in meaningful quantities. Even if Japan had possessed the industrial capacity, there was a timing problem. Developing and fielding new weapon systems requires years. The Mark 8 fire control system had been in development since the late 1930s, with earlier rangekeeper versions dating to World War I. This was evolutionary technology, refined over decades through systematic research and testing. You couldn't just copy it and expect it to work. You needed the institutional knowledge, the trained personnel, and the supporting industrial infrastructure. This time, lag between technological development and fielding has been a constant factor in military competition. The side that invests early in emerging technologies gains advantages that opponents cannot quickly overcome. By the time Japan recognized how critical radar and fire control integration were, American systems were already operational throughout the fleet. Japanese efforts to develop comparable systems came too late to affect the war's outcome. The fire control systems also benefited from broader American strengths in electronics and precision manufacturing. Companies like IBM, which had been producing mechanical calculators and tabulating machines for decades, brought expertise in precision manufacturing to military contracts. Sperry Corporation, known for gyroscopes and navigational equipment, contributed stabilization technology. The integration of expertise from multiple industries created systems more sophisticated than any single company could have developed. This integration of civilian and military research accelerated innovation dramatically. Techniques developed for fire control computers found applications in analog computing for aircraft instruments, anti-aircraft predictors, and even early automated factory machinery. the war years saw extraordinary cross-pollination of ideas between military and civilian engineering. Fire control problems inspired new mathematical techniques that later found use in control theory and systems engineering. The human factors of these systems were as carefully designed as the mechanical components. Control panels were laid out based on extensive testing of what arrangements allowed operators to work most efficiently under stress. Critical indicators used contrasting colors and large fonts readable in poor lighting. Emergency backup procedures were designed so that if the computer failed, the system could revert to manual operation. Every aspect reflected careful thought about how humans and machines would work together. Operating a fire control system required a crew of specialists working in coordination. The radar operator maintained the lock on target, ensuring the beam stayed centered on the return signal. The rangekeeper operator input tactical data like target speed and course, updating these estimates as new information became available. The plotting room team maintained manual backups, tracking targets on paper charts in case electronics failed. Gun captains in each turret supervised loading and firing. The gunnery officer oversaw the entire process, making decisions about target selection and engagement priorities. This distributed team approach meant that losing individual operators didn't cripple the system. If the radar operator was killed or wounded, another crew member could take over. If the rangekeeper failed, manual procedures allowed continued operation at reduced effectiveness. This redundancy and resilience reflected American design philosophy. Systems should degrade gracefully under damage, not fail catastrophically. Combat damage control was extensively planned. Fire control systems had protected backup power supplies. Critical cables were run through multiple paths so a single hit couldn't sever connections. Key components had spares stored nearby for quick replacement. American warships were designed to take damage and keep fighting, with fire control systems receiving particular attention, because their loss meant the ship became ineffective even if guns remained operational. The Battle of Samar on October 25, 1944, the same day as Surigao Strait, demonstrated both the capabilities and limitations of fire control technology. American escort carriers and destroyers faced Japanese battleships and cruisers in a surface action. The American destroyers, equipped with Mark IA fire control computers, engaged at ranges where their 5-inch guns were at maximum elevation. The computers calculated solutions for these extreme-range shots, lobbing shells on high arcs toward targets over 18,000 yards away. USS Johnston, commanded by Commander Ernest Evans, scored hits on the heavy cruiser Kamano from over 10,000 yards using her Mark IA fire control system. The computer maintained the targeting solution even as Johnston maneuvered violently to avoid incoming fire. This ability to maintain accurate fire while performing evasive maneuvers would have been impossible with manual gun laying. The computer automatically compensated for the ship's motion, keeping guns trained on target even as Johnston twisted and turned. However, the engagement also showed that fire control technology couldn't overcome overwhelming force. Japanese ships eventually surrounded and destroyed Johnston along with other American destroyers. Superior technology provided advantages, but it didn't guarantee victory against determined enemies with numerical superiority. The American ships fought far more effectively than they could have without automated fire control, but there were limits to what technology could achieve. The limitations of mechanical computing also became apparent in complex scenarios. The Mark 8 rangekeeper could track one target at a time. If you wanted to engage multiple targets simultaneously, you needed multiple fire control systems, or had to rapidly switch between targets, which introduced delays and reduced effectiveness. Later electronic systems would eliminate this limitation, but World War II-era mechanical computers couldn't process multiple targets simultaneously. Range was another limitation. Even with radar, maximum effective range was constrained by the ballistic performance of the guns themselves. The 16-inch guns of Iowa-class battleships could fire shells about 42,000 yards, roughly 24 miles. Beyond that range, even perfect fire control couldn't help because the projectiles physically couldn't reach. Fire control technology extended effective range to the gun's maximum, but it couldn't exceed those physical limits. Shell dispersion also limited practical effectiveness at extreme ranges. Even when fired at identical angles, shells didn't follow exactly the same trajectories due to minor variations in powder charge, projectile weight, and barrel condition. At extreme ranges, this dispersion meant that even with perfect fire control, multiple shells from the same salvo could land hundreds of yards apart. Hitting a target at 40,000 yards required multiple salvos to bracket the target and walk fire onto it. Fire control computers made this process faster and more systematic, but they couldn't eliminate the fundamental physics of dispersion. Weather effects introduced additional complications. Wind at different altitudes affected shell trajectories in complex ways. Barometric pressure variations changed air density. Temperature affected powder performance. The most sophisticated fire control systems included inputs for these meteorological factors, but the data available was imperfect. Ships used weather balloons and detailed logs of atmospheric conditions, but predicting exactly how wind at 30,000 feet would affect a shell was still partially art rather than pure science. Despite these limitations, the practical effectiveness of American fire control systems was revolutionary. Comparing hit rates before and after radar integration reveals the dramatic improvement. In exercises conducted in the 1930s using optical rangefinders and manual calculation, hit rates against maneuvering targets at 20,000 yards range from 2 to 5%. By 1944, with radar-directed fire, hit rates exceeded 15% under similar conditions. That threefold improvement meant that engagements that would have required hundreds of shells now needed dozens. Ammunition efficiency increased dramatically. The economic implications were significant. High explosive shells for battleship main batteries cost thousands of dollars each in 1940s money. Improving hit rates meant less ammunition consumption for the same effect. This translated to reduced logistics burden. Ships could carry fewer shells while maintaining effective combat capability. Ammunition ships could support more vessels. The entire logistics chain became more efficient. Better technology didn't just improve combat effectiveness, it reduced the costs of achieving military objectives. The strategic implications extended beyond individual battles. Control of sea lanes depended on the ability to locate and destroy enemy surface forces. Radar and fire control systems dramatically increased the probability that any encounter between American and Japanese surface forces would result in American victory. This shifted the strategic calculation. Japanese commanders knew they faced long odds in surface engagements, which influenced their operational planning. The Japanese Navy increasingly emphasized submarine warfare, aviation, and eventually kamikaze attacks. These represented attempts to find asymmetric advantages that didn't require them to match American technological superiority in surface gunnery. Submarines could attack without being seen. Aircraft could strike from ranges where ship-to-ship gunnery was irrelevant. Suicide attacks didn't require returning alive, eliminating the need for sophisticated fire control or navigation equipment. This pattern of technological advantage forcing adversaries toward asymmetric responses has recurred throughout military history. When one side achieves dominance in conventional capabilities, opponents seek alternative methods. The American advantage in radar-directed gunnery helped drive Japanese desperation tactics in late 1944 and 1945. Unable to win conventional surface engagements, they turned to methods that bypassed American advantages. The post-war period saw rapid evolution of fire control technology as mechanical systems gave way to electronic computers. The Mark IA Rangekeeper, despite being mechanical, remained in service through the 1970s on some ships because it worked reliably and crew members understood it thoroughly. The transition to electronic systems was gradual, with mechanical computers serving alongside early digital systems during the 1950s and 1960s. The lessons learned from mechanical fire control influenced early electronic computer design. Engineers familiar with rangekeepers understood concepts like feedback loops, error correction, and real-time processing. When they began designing electronic computers for military applications, they brought these concepts with them. Many early digital fire control systems were essentially electronic implementations of Rangekeeper logic, performing the same calculations but using vacuum tubes and transistors instead of gears and cams. The reliability challenges in transitioning from mechanical to electronic systems were substantial. Mechanical computers were robust and predictable. A gear either turned or it didn't. Electronic computers using early vacuum tubes were temperamental. Tubes burned out, requiring frequent replacement. Electronic components were sensitive to temperature, humidity, and vibration. Early digital fire control systems were actually less reliable than the mechanical systems they replaced. It took decades of development before electronic systems achieved reliability matching mechanical predecessors. The transition to solid-state electronics in the 1960s finally provided the durability needed for naval applications. Transistors were more reliable than vacuum tubes and consumed less power. As integrated circuits became available in the 1970s, electronic fire control systems became both more capable and more reliable than any mechanical system could be. Modern naval fire control is almost unrecognizable compared to World War II systems. Current systems use phased array radars that can track hundreds of targets simultaneously. Digital computers process millions of calculations per second. Automated systems can identify targets, classify them as hostile or friendly, prioritize threats, calculate engagement solutions, and fire weapons entirely autonomously if authorized. A modern destroyer can engage aircraft, missiles, and surface targets simultaneously while tracking everything within hundreds of miles. But the fundamental principles established in World War II-era systems remain. Sensors detect targets beyond human perception. Computers predict future positions. Automated systems aim and fire weapons. Human operators supervise and make engagement decisions. The technology has evolved enormously, but the paradigm established when radar first integrated with mechanical computers persists. The veterans who operated these systems during World War II witnessed a transformation they could never have imagined. Men who had trained in traditional naval gunnery, learning to estimate range by eye and judge target motion by observation, suddenly found themselves operating complex electromechanical systems that did the thinking for them. The adjustment was not always easy. Some officers distrusted the machines, believing that seamanship and experience should matter more than technology. But combat results proved the value of automation. Ships with well-maintained fire control systems and trained crews consistently outperformed those relying on traditional methods. The human element remained critical in operating the systems, but the systems themselves provided capabilities no amount of human skill could match. You couldn't train optical rangefinder operators to see through darkness, or calculate range to 40,000 yards with accuracy of 50 yards. The machines could. The fire control technicians who maintained these systems became some of the most valuable specialists in the fleet. A skilled FC tech, as they were called, could mean the difference between a ship that fought effectively and one that became a liability. These technicians worked long hours in cramped plotting rooms, ensuring that every component was properly lubricated, aligned, and calibrated. Their work was largely invisible to the rest of the crew, but it was absolutely critical to combat effectiveness. Many fire control technicians recalled the immense pressure they felt before action. Knowing that the accuracy of the ship's gunnery depended on your maintenance and calibration created intense responsibility. If you had missed something during your inspection, if a gear was slightly misaligned or a connection was loose, men could die because shells would miss their targets. This psychological burden was significant, though it was rarely discussed publicly. The success of American fire control systems has often been overlooked in popular histories of World War II, which tend to focus on more dramatic elements like carrier battles and amphibious assaults. But the technological superiority represented by radar-directed automated gunnery was as significant as any other factor in the Pacific War. It gave American forces decisive advantages in surface combat that Japanese forces could never overcome. When analyzing why the United States won the Pacific War, historians typically emphasize industrial capacity, resource access, and numerical advantages. These factors were indeed critical, but technological superiority in key areas like radar, fire control, and damage control was equally important. Having more ships mattered, but having ships that could fight more effectively per unit multiplied that advantage. The integration of radar and fire control computing represents an early example of what modern military strategists call force multiplication. A single battleship with Mark 8 fire control was worth several ships without it in terms of combat effectiveness. This meant that even when Japanese forces achieved local numerical parity, they faced American forces that were effectively superior due to better technology. The multiplication effect of better sensors and computing power was dramatic. The development of these systems also highlighted the importance of sustained investment in research and development. The United States Navy had been working on fire control computing since World War I. This quarter-century of continuous development created institutional knowledge and industrial capability that couldn't be quickly replicated. Nations that neglected this investment found themselves unable to catch up when war came. The same pattern has repeated in subsequent military competitions. The side that invests consistently in emerging technologies gains advantages that become difficult for opponents to overcome. The decades of American investment in stealth technology, precision-guided munitions, and satellite navigation during the Cold War created capabilities that adversaries still struggle to match. The investment compounds over time, with each generation of technology building on previous foundations. Looking back from today's perspective, the mechanical fire control computers of World War II seem almost quaint. We carry more computing power in our smartphones than existed in the entire Mark 8 system. Modern weapon systems use artificial intelligence and machine learning in ways that would seem like magic to 1940s engineers. But the fundamental breakthrough those systems represented, extending human capability through automated computing, was revolutionary. Admiral Willis Lee, who commanded USS Washington during the naval Battle of Guadalcanal, didn't live to see the ultimate vindication of the technology he had championed. He died in August 1945 from a heart attack, just days before Japan surrendered. But his advocacy for radar and automated fire control had helped push the Navy to adopt and refine these systems. His willingness to trust the technology during the critical engagement on November 14, 1942, demonstrated that it could work in combat, encouraging wider adoption throughout the fleet. The sailors who served on USS West Virginia at Surigao Strait, many of whom had been aboard during the Pearl Harbor attack, experienced perhaps the most dramatic demonstration of technological revenge in military history. The ship that had been sunk by surprise attack had been raised, rebuilt, and equipped with technology that made surprise impossible. When she engaged Yamashiro from beyond visual range in total darkness, it represented not just a tactical victory but a symbolic one. Technology had transformed defeat into overwhelming superiority. The mechanical fire control computers that made these victories possible were retired from service decades ago. The last Mark IA Rangekeeper was decommissioned in the mid-1970s when the last gun-armed cruisers left the fleet. These machines, which had served faithfully through World War II, Korea, and Vietnam, were finally replaced by electronic systems that could perform the same functions faster and more accurately. Many were scrapped, though some survive in museums as testament to the sophistication of pre-electronic computing. The men who built these machines, engineers and machinists at companies that no longer exist or have long since changed their focus, created weapons that helped win a world war. Their names are largely forgotten, appearing in no history books and commemorated by no monuments. But their work represented one of the most successful military technology programs ever conducted. From concept to deployment to combat effectiveness, the Fire Control Computing Program delivered exactly what it promised. Ships that could fight and win beyond the horizon, in darkness, in conditions where human eyes were useless. The story of American naval fire control computers is ultimately a story about how technology changes warfare at fundamental levels. For all of human history, combat was limited by human sensory and cognitive capabilities. You could only fight what you could see, and you could only aim where you could calculate. Radar and computing broke those limitations. Ships could see electronically through darkness. Computers could predict the future with mathematical precision. Machines could aim weapons with accuracy impossible for human gunners. This extension of human capability through technology has only accelerated since World War II. Modern warfare is increasingly fought by sensors and computers, with humans supervising systems that operate at speeds and ranges where unaided human perception cannot function. Drones fly missions controlled by operators thousands of miles away. Missiles navigate themselves to targets using GPS and terrain matching. Ships defend themselves with automated systems that detect and engage threats faster than human crews could respond. All of this traces back to those first radar-directed engagements in 1942 and 1944. When USS Washington fired into the darkness at an enemy visible only on a cathode ray tube, when USS West Virginia's guns followed commands from a mechanical computer to strike a target 24 miles away, they demonstrated a new paradigm. The age of visual combat was ending. The age of electronic warfare was beginning. The thunder of those 16-inch guns in the darkness of Iron Bottom Sound and Surigao Strait announced the arrival of a new era. An era where technology would matter more than tradition, where sensors would matter more than eyesight, where computing would matter more than human calculation. The ships that were sunk beyond the visible horizon didn't just lose battles. They represented the end of an age when warfare was conducted at human scale. The machines had arrived, and warfare would never be the same again. The story of American fire control supremacy extended beyond the Pacific battles. In November 1942, USS Massachusetts participated in Operation Torch, the Allied invasion of North Africa. On November 8th, while steaming off Casablanca, Morocco, Massachusetts engaged the French battleship Jean Bart in what would become the first combat test of American fire control technology against a modern European battleship. Jean Bart was incomplete, lacking engines and unable to move from her berth at the harbour pier. But her main battery of 4 15-inch guns in 2 turrets was operational, and her French crew was prepared to defend Vichy-controlled Morocco against the American invasion. At 7:04 in the morning, Jean Bart opened fire at Massachusetts from her protected harbour position. The French battleship's shore-based fire control system, operating with optical rangefinders, was adequate for the static engagement. But Massachusetts possessed advantages that Jean Bart's gunners couldn't match. The American battleship's Mark 8 fire control radar had acquired Jean Bart at ranges where optical systems struggled in the dawn light. Massachusetts returned fire at 7:40, launching the first 16-inch shells fired by the United States against Axis or Axis-aligned forces in World War II. The engagement was brief, but decisive. Massachusetts's fire control system, even without radar integration at this early stage of the war, demonstrated superior accuracy. Within minutes, 5 16-inch armour-piercing shells struck Jean Bart, with at least one penetrating her forward turret. The French battleship's main battery fell silent, knocked out by the concentrated American fire. The engagement demonstrated something critical about American fire control philosophy. Even ships like Massachusetts, which had been commissioned just months earlier and were still working up their systems, could achieve devastating accuracy through systematic application of fire control computing. The rangekeeper continuously refined its solution with each salvo, using shell splashes to correct for errors. This systematic approach, where machines handled the mathematical heavy lifting while humans supervised and made tactical decisions, proved more effective than systems relying primarily on experienced gunners and manual calculation. Massachusetts went on to fire at shore batteries and helped sink 2 French destroyers that attempted to sortie from Casablanca harbour. In the entire engagement, American fire control achieved hit rates that would have been considered exceptional, even under peacetime target practice conditions. The battleship had proven that the technology worked not just in theory, but in actual combat against a determined enemy. After North Africa, Massachusetts transferred to the Pacific, where she would spend the rest of the war. Her subsequent service validated the fire control systems under every imaginable condition. In the Gilbert and Marshall Islands campaigns, she provided naval gunfire support for amphibious assaults, using her radar and computing systems to accurately place shells on Japanese defensive positions. During the Battle of Leyte Gulf in October 1944, she screened fast carriers, using her fire control systems to engage Japanese aircraft attempting to attack the task force. The versatility of American fire control systems became apparent in these varied missions. The same computing technology that allowed precision engagement of moving ships at sea could be adapted for shore bombardment. The rangekeeper could calculate the ballistics for stationary targets with even greater precision than for moving vessels. Operators simply set target speed to 0 and adjusted for the ship's own motion. The result was naval gunfire that could hit targets inland with accuracy approaching that of land-based artillery. In July and August 1945, Massachusetts participated in the final bombardment of the Japanese home islands. Her 16-inch guns, guided by fire control, computers and radar, struck industrial targets on Honshu with devastating precision. On August 9, 1945, Massachusetts fired what is believed to be the last 16-inch shell of World War II at the Kamaishi Iron and Steel Works. From the first shells at Casablanca to the last at Kamaishi, Massachusetts had demonstrated American fire control supremacy across 3 years of global warfare. The evolution of fire control technology during the war years was rapid and continuous. Engineers at Ford Instrument Company and associated contractors constantly refined the systems based on combat experience reports. early war rangekeepers required significant manual input from operators. Mid-war versions incorporated more automation, with radar data feeding directly into the computers with less human intervention. Late-war systems added features like automatic target selection, allowing the fire control computer to switch between multiple targets based on tactical priorities. The Mark IA fire control computer, which saw extensive service on cruisers and some battleships, represented the culmination of mechanical computing technology. Weighing approximately 2,800 pounds, it contained over 20 servo motors, more than 160 synchros for data transmission, hundreds of precision gears, and dozens of integrators and differential mechanisms. Every component was machined to tolerances measured in thousandths of an inch. The entire assembly could solve complex differential equations continuously, updating gun orders 30 times per second. Operating a Mark IA required extensive training. Fire control technicians attended specialized schools where they learned not just how to operate the system, but how it worked at a fundamental mechanical level. They studied gear trains, learned to diagnose failures by sound and vibration, practiced emergency repair procedures, and memorized hundreds of technical specifications. The best technicians could identify problems by observing the motion of indicator dials or listening to the sounds the machine made under operation. This investment in training created a cadre of specialists who understood analog computing at an intuitive level. Many of these technicians went on to careers in the emerging electronic computing industry after the war. The troubleshooting skills they developed, the systematic approach to complex problems, and the understanding of feedback systems translated directly to working with early electronic computers. The bridge between mechanical and electronic computing was built by people who had maintained rangekeepers under combat conditions. The reliability of these mechanical systems under combat stress was remarkable. Ships took battle damage that destroyed portions of their fire control systems, yet the redundancy built into the designs often allowed continued operation at reduced capability. If the main fire control computer was damaged, backup manual systems could be engaged. If radar was knocked out, optical, rangefinders could feed data to the computer. If power was lost to servo motors, guns could be manually trained to the angles displayed on indicators. The systems degraded gracefully rather than failing catastrophically. USS South Dakota, which fought alongside Washington at Guadalcanal, experienced this graceful degradation firsthand. During the November 14th engagement, electrical failures knocked out much of her fire control system. Her radar went dark. Her main battery rangekeeper lost power, but her crew improvised, using emergency backup procedures and manual gun laying to continue fighting. Though significantly less effective than with full automation, South Dakota remained in the fight. This resilience, built into the design from the beginning, meant that American ships could continue engaging even after sustaining damage that would have completely disabled ships lacking redundant systems. The contrast with Japanese fire control philosophy was stark. Japanese systems emphasized human skill and training over automation. Their excellent optical equipment and well-drilled crews could achieve impressive results under ideal conditions, but Japanese systems lacked the redundancy and automation of American designs. When conditions became difficult, when visibility dropped, or targets maneuvered unpredictably, Japanese accuracy degraded rapidly. Their fire control required multiple operators working in coordination, and losing any of those operators significantly impaired effectiveness. German fire control systems, while sophisticated, suffered from different limitations. German rangekeepers were complex and capable, but they weren't integrated with radar to the extent American systems were by 1943. German warships had radar for detection and ranging, but fire control still relied heavily on optical systems and manual data input. The Kriegsmarine had invested heavily in optical excellence, producing rangefinders and directors that were engineering masterpieces. But optical systems, no matter how sophisticated, couldn't overcome the fundamental limitation of human eyesight. The British Royal Navy developed fire control systems that were comparable to American designs in many respects. British fire control computers, particularly those developed by Admiralty fire control table designs, could perform sophisticated calculations. But British systems often lagged behind American designs in integration and automation. The close cooperation between British and American naval forces during the war led to extensive technology sharing, with both navies benefiting from each other's innovations. What truly set American fire control apart wasn't any single technological breakthrough, but the systematic integration of multiple technologies into a unified whole. Radar provided precise range and bearing data. Gyroscopic stabilizers maintained a true vertical reference despite ship motion. Analog computers solved the ballistic equations continuously. Servo mechanisms aimed the guns automatically. Redundant systems provided backup capability. Extensive training ensured crews could operate and maintain the technology. This systems approach, where every component supported every other component, created capability greater than the sum of the parts. Modern military theorists use the term system of systems to describe this integrated approach. The fire control system wasn't just the rangekeeper computer. It was the radar, the stabilizers, the servos, the data transmission network, the backup systems, the trained operators, the maintenance procedures, and the tactical doctrine for employing all of it effectively. American success came from optimizing the entire system, rather than just producing excellent individual components. This systems approach required institutional capabilities beyond just industrial production. It required research laboratories where scientists could investigate fundamental questions about radar, ballistics, and computing. It required testing facilities where prototypes could be evaluated under controlled conditions. It required doctrine developers who understood how to employ new capabilities tactically. It required training establishments that could educate thousands of specialists. The entire institutional ecosystem had to function effectively for the technology to reach its full potential. The United States possessed this institutional ecosystem. MIT's Radiation Laboratory developed radar innovations that fed directly into fire control applications. The Naval Research Laboratory investigated electromagnetic propagation and computing techniques. The Naval Proving Ground tested fire control systems extensively. The Naval Ordnance Test Station evaluated ballistic performance. The Naval War College developed tactical doctrine for employing new capabilities. This network of institutions working in coordination accelerated innovation dramatically. Japan and Germany possessed excellent scientists and engineers, but they lacked the institutional depth of American research and development establishment. Japanese universities produced capable physicists and engineers, but far fewer than American institutions. German research was world-class in many areas, but the Nazi regime's persecution of Jewish scientists had devastated their scientific community. The institutional advantages that America possessed in 1941 compounded over time, as each generation of technology built on knowledge gained from the previous generation. The economic factors were equally significant. Developing and fielding sophisticated fire control systems required enormous investment. Each rangekeeper cost over $1 million in 1940s currency. The supporting systems, radar, servos, stabilizers, added similar costs. Training the specialists to operate and maintain the equipment required extensive infrastructure. The ammunition required for the systems to fire required millions of high-precision shells. The total investment in naval fire control across the fleet ran into billions of dollars. The United States could afford this investment while simultaneously building thousands of ships, tens of thousands of aircraft, and millions of tons of other war material. The American economy in 1943 and 1944 was producing more war material than all other combatants combined. This overwhelming economic capacity meant that cost was rarely a limiting factor in American military development. If a technology would improve combat effectiveness, funding could be found to develop and field it. For other nations, cost imposed real constraints. Japan's economy was a fraction of America's size, and Japanese industrial capacity was stretched to breaking point trying to build and fuel a fleet large enough to contest the Pacific. Investing in sophisticated fire control computers meant diverting resources from other needs. German industrial capacity was larger than Japan's, but was being consumed by the demands of fighting on multiple fronts. Every mark spent on naval fire control was a mark not spent on tanks or aircraft or submarines. These economic constraints meant that American forces often fought with qualitative advantages in addition to quantitative superiority. American ships were individually more capable due to better technology, and there were more of them. This combination proved overwhelming. By 1944, Japanese commanders understood that any surface engagement with American forces would be one-sided. The technology gap had become so wide that tactical skill couldn't bridge it. The psychological impact on Japanese sailors was profound. and is often underestimated in historical accounts. Accounts from Japanese survivors describe the terror of facing American radar-directed fire. Shells would arrive from darkness with no warning. There was no muzzle flash to see, no sound of gunfire to hear, just sudden explosions as projectiles impacted around their ships. The experience was deeply demoralizing. Sailors trained to fight bravely found themselves helpless against invisible enemies they couldn't locate or engage. This psychological advantage complemented the technological superiority. American sailors fought with confidence born from knowing their equipment was superior. They had radar that could see in darkness. They had computers that could hit targets beyond visual range. They had armor that could withstand punishment. This confidence translated into better performance under stress. Japanese sailors, conversely, fought with the knowledge that they were technologically outmatched. This affected morale, decision-making, and ultimately combat effectiveness. The doctrine for employing fire control systems evolved throughout the war based on combat experience. Early doctrine treated radar as a supplement to optical systems. Commanders still expected to fight primarily using visual target acquisition, with radar providing support. But battles like Guadalcanal demonstrated that radar could be the primary sensor with optical systems relegated to backup. Doctrine evolved to reflect this reality. By 1944, standard doctrine for night surface engagements relied almost entirely on radar. Optical systems were kept manned as backup, but radar provided target detection, ranging, and fire control. Commanders planned night actions knowing they could fight effectively in total darkness. This changed tactical calculations fundamentally. Previously, night battles were chaotic affairs where both sides struggled with limited visibility. Now, American forces could operate at night nearly as effectively as in daylight. The advantage extended to weather conditions. Fog, rain, and smoke that would blind optical systems had minimal effect on radar. American warships could fight in conditions where Japanese ships were effectively blind. This weather independence gave American commanders tactical flexibility. They didn't need to wait for good visibility to engage. They could press attacks in any conditions, knowing their fire control would work regardless of visibility. Shore bombardment doctrine also evolved dramatically. Pre-war concepts assumed that naval gunfire against land targets would be relatively inaccurate, useful for saturating areas but not for precision strikes. But combat experience showed that radar and fire control computers could deliver precision even against shore targets. By 1944, naval gunfire was being used like flying artillery, hitting specific buildings, bunkers, and gun emplacements with accuracy measured in yards rather than hundreds of yards. This precision naval gunfire support became critical during amphibious operations. Marines assaulting Pacific islands faced heavily fortified Japanese defensive positions. The ability to call in accurate naval gunfire that could hit targets close to friendly forces proved invaluable. Fire control systems that could reliably place shells within 50 yards of a designated target allowed naval gunfire to be used throughout the assault, not just in preliminary bombardment. The fire control officer coordinating shore bombardment became a critical specialist. He needed to understand the computer's capabilities and limitations, coordinate with spotters ashore providing target information, and manage ammunition expenditure. Good fire control officers could keep multiple fire missions running simultaneously, shifting guns between targets as priorities changed. This required understanding both the technical systems and the tactical situation, making fire control officers some of the most valuable specialists aboard ship. The complexity of the role reflected the complexity of the technology. Fire control was no longer simply pointing guns and firing. It was managing an integrated information and weapon system. It required technical knowledge, tactical understanding, and decision-making under intense pressure. The best fire control officers were those who understood the machinery so well that they could push it to its limits without exceeding them. Stories from veterans who operated these systems reveal the intense focus required. Radar operators had to maintain their concentration for hours, watching screens for targets while filtering out clutter from waves, rain, and other ships. Rangekeeper operators had to continuously refine their solutions, adjusting target course and speed estimates as new information became available. Gun crews had to respond instantly to fire commands, loading and firing as quickly as possible while the solution remained valid. Every person in the chain had to perform their role precisely for the system to achieve its full potential. The teamwork required was extraordinary. A battleship fire control crew could include dozens of specialists, from radar operators in the director stations high on the superstructure to plotting room crews deep in the armoured citadel to gun crews in the turrets. They communicated through sound-powered phones and data transmission lines, coordinating actions while separated by hundreds of feet of steel structure. This distributed team had to function as a unified whole, with each member trusting that others would perform their roles correctly. Training exercises emphasized this teamwork. Ships conducted countless practice shoots, firing at targets, while the entire fire control team worked together to achieve hits. After each shoot, the crew would analyze the results, identifying errors and refining procedures. This continuous improvement process, where combat experience and training fed back into improved techniques, kept American fire control effectiveness increasing throughout the war. The competitive spirit among fire control crews drove excellence. Ships competed for the highest scores in gunnery competitions, with winning crews receiving recognition and pride. This competition motivated crews to master their systems and develop innovative techniques. Some of the best tactical procedures came from creative crews finding better ways to employ their equipment. These innovations would be shared across the fleet, raising overall performance. The integration of fire control systems with broader combat information centers represented another major innovation. Early in the war, fire control plotting rooms focused exclusively on solving gunnery problems. But as radar provided more comprehensive information about the tactical situation, ships developed centralized combat information centers that tracked all contacts, friendly and enemy. These CICs became the nervous system of the ship, processing information from multiple sensors and distributing it to weapon systems. The fire control computer connected to CIC received not just information about the current target, but the complete tactical picture. This allowed better target selection and engagement prioritization. If the computer was tracking one target but CIC identified a higher priority, threat control could switch quickly. This integration of sensors, computing, and weapons into a unified information network was a preview of modern combat systems. By war's end, the most advanced American warships had combat systems that would seem familiar to modern naval officers. Centralized radar provided the tactical picture. Computers processed information and generated weapon solutions. Automated systems aimed and fired weapons. Human operators supervised the process and made tactical decisions. This human-machine partnership, refined through years of combat, established patterns that persist in naval warfare today. The legacy of World War II fire control technology extends far beyond naval applications. The techniques developed for tracking moving targets and predicting their future positions found applications in air defense systems, where the problem was similar but with faster-moving targets. Post-war development of guided missiles built on fire control computing, with missiles essentially being computer-controlled projectiles that could adjust their trajectories in flight. The Cold War missile age transformed naval warfare again, but it built on foundations laid by World War II fire control development. The Aegis combat system, which revolutionized naval warfare in the 1980s, was a direct descendant of World War II fire control concepts. Aegis used radar to track targets, computers to calculate weapon solutions, and automated systems to engage threats. The technology was revolutionary, using phased array radar and digital computing, but the conceptual framework came directly from experiences with ships like Washington and West Virginia. Today's naval officers studying the fire control engagements of World War II recognize the parallels to modern systems. The fundamental problems remain the same: detect targets beyond visual range, calculate where they'll be when weapons arrive, aim weapons to hit that predicted position. The tools have changed dramatically, from mechanical computers to quantum processors, from vacuum tube radar to phased arrays, from gun projectiles to hypersonic missiles. But the underlying logic persists. The men who developed and operated World War II fire control systems created more than just weapons. They established the paradigm for how modern warfare is conducted. They demonstrated that technology could extend human capability beyond natural limitations. They showed that systematic, automated approaches could outperform human skill and intuition. They proved that investing in complex, expensive technology paid dividends in combat effectiveness. Standing on the deck of a preserved battleship like USS Massachusetts or USS North Carolina, visitors can see the physical remnants of this revolution. The massive radar directors, now silent, once swept the horizons, detecting targets dozens of miles away. The optical rangefinders, their lenses dimmed with age, supplemented electronic eyes. Below decks, the fire. Control plotting rooms contain the mechanical computers that turned sensor data into weapon solutions. These artifacts tell a story of technological transformation. But the real story isn't visible in the hardware, it's in the invisible revolution these systems represented. For the first time, warfare could be conducted beyond human sensory limits. For the first time, machines could calculate faster and more accurately than human minds. For the first time, automation could outperform manual skills honed through years of practice. The paradigm shift that began when USS Washington fired at invisible targets in the darkness of Guadalcanal has continued accelerating ever since. We live in the world that revolution created, a world where warfare is increasingly automated, where sensors detect threats beyond human perception, where computers make decisions faster than humans can think. The ethical and strategic questions raised by autonomous weapons, artificial intelligence in combat, and the role of human judgment in automated warfare all trace back to those first engagements, where fire control computers directed guns at targets no human eye could see. The sailors who operated those early systems would be astonished by modern weapons, but they would recognize the fundamental principles, detect the target, calculate the solution, engage automatically. The technology has evolved beyond anything they could have imagined, but the logic they pioneered persists. When USS Washington's guns thundered in the darkness of November 1942, they announced more than the presence of American naval power. They announced the arrival of a new age in human conflict, an age where machines would increasingly handle the tasks that humans could not. That age has continued unfolding, and we still live in its shadow.